So back in the 1980s, researchers actually gathered a room full of university calculus and engineering students.
Right, so people who are very, very good at math.
Exactly, I mean, advanced students. And they gave them a single, straightforward sentence, just asking them to translate it into a basic algebra equation. And, well, a full one-third of them completely failed.
Yeah, it's wild. They wrote down an equation that literally stated the exact opposite of reality.
Which is just crazy to think about. Today, we're looking at why that happened, and more importantly, how to make sure it doesn't happen to you.
Because it is such an easy trap to fall into.
It really is. So whether you are, a nursing student studying for the TEAS or his HESI exam right now, or you're just a curious learner wanting to bulletproof your own quantitative reasoning, this deep dive is for you.
Absolutely.
Because today, our mission is to unpack the hidden, honestly surprising complexities of translating words into equations. We are going from sentence to symbol. We're going to show you why turning a word statement into a math equation is rarely as simple as just, hunting for a plus sign.
Right, because math isn't just a collection of numbers, it's a distinct language.
Yeah. And like any language, things get drastically lost in translation. We are pulling from comprehensive educational notes on exam prep today, diving into the cognitive science behind why our brains basically glitch on these problems. Plus, the history of algebra and the practical life-or-death applications in fields like nursing.
Yeah, to understand why this is so difficult, we first need to define what translation actually is versus, what we think it is.
Right. What it appears to be.
Exactly. Most test takers treat this like a basic word search. You see the word sum, you write a plus sign. You see the word is, you write an equal sign. It's just a very surface level left to right swap.
Okay, let's unpack this because this sounds like translating a foreign language using a cheap pocket dictionary.
Oh, that's a great way to put it.
Like if I go to France and just swap English words for French words one for one without understanding the underlying grammar, I'm going to end up speaking absolute nonsense. I mean, you have to grasp the actual meaning of the sentence before you can translate it.
That analogy gets right to the heart of it, honestly. In mathematics, we call that meaning building semantic modeling.
Semantic modeling.
Yeah. You have to encode the logical structure of the sentence, not just its vocabulary. And to do this correctly from first principles, there are 3 sequential moves you must make. And none of them involve just reading left to right.
Wait, none of them?
No. First, you identify the unknowns and assign variables.
Okay, so that's your classic let statement, like let X represent the dosage.
Exactly, that's move 1. Second, you identify the operations and the relationships between those variables. And third, crucially, you preserve the exact logical structure of those relationships.
I can see why people hate doing that. It is cognitively demanding. It's so much easier to just use the cheap dictionary.
Oh, for sure. It takes effort.
And to be fair, sometimes the cheap dictionary actually works. Like if a test question says 6 times a number is 18, I can just read left to right. 6 is 6, times is multiply, a number is n, means equals, and 18 is 18, so 6n equals 18.
Right. It works perfectly there.
I didn't build a semantic model at all.
Right.
I just swapped symbols.
Which is exactly why the problem is so insidious. Those basic warm-up questions on the TEAS and HESI exams, they actively train your brain to rely on that lazy left-to-right syntactic mapping.
Oh, wow. So they're setting us up to fail later.
They reward you for using the cheap dictionary. But the moment the relationship becomes comparative, that strategy fails catastrophically. Which, brings us back to those calculus students in the 1980s.
Yes. Let's get into this famous failure. You have a room full of engineering and calculus students, people who definitely know their way around complex math. What was the exact sentence the researchers gave them?
So the researchers, John Clement, Jack Lockhead, and Donald Monk, gave them this statement. There are 6 times as many students as professors at this university.
Okay.
And they were told to write an equation using S for the number of students and P for the number of professors.
Let me think about this. 6 times as many students as professors. My immediate instinct, using my cheap mental dictionary, is to read the word 6, see the word students, and just write 6S.
Naturally.
Then I put an equal sign and put P for professors on the other side. So 6S equals P.
And you would be right in the company of 1/3 of those advanced calculus students. 6S equals P was the most common wrong answer.
Wait, wrong answer. Let me actually build the semantic model for a second and think about what I just wrote.
Go for it.
If S is the number of students, let's pretend there are 10 students. 6 times 10 is 60. So in my equation, P equals 60.
Mm-hmm.
I just created a university with 10 students and 60 professors. That is completely backward.
You created a reality where the professors massively outnumber the students, despite the sentence explicitly stating the exact opposite.
Oh man, that's wild. So what's the correct equation?
The correct equation is actually S equals 6p. Because the students outnumber the professors, you have to multiply the smaller quantity, the professors, by 6 in order to scale it up and balance the equation with the larger quantity of students.
S equals 6p. I mean, that feels incredibly uncomfortable to write. My brain is physically fighting it.
It does. It feels wrong.
Because the sentence starts with the number 6 right next to the word students.
Yeah.
Writing the 6 next to the p feels like I am violating the text. So what does this all mean? Is this just sloppiness on the part of the test taker, or is something deeper happening in the brain?
It's a profound psychological friction, actually, and it sparked a massive debate in math education. John Clement, the original researcher, proposed what he called the syntactic mapping hypothesis.
Which means what, exactly?
He argued that students are operating like Google Translate 1.0. They are mapping word order directly into symbol order, just completely bypassing the semantic meaning.
Right, the cheap dictionary.
Exactly. But a decade later, researchers Molly McGregor and Case Stacy offered a really fascinating rival view. They argued this isn't just lazy math, it's actually an overgeneralization of natural language reading strategies.
Okay, wait, what does that mean in practice?
Well, think about standard English grammar. If I say 6 students per professor, how do you read that?
I read it left to right.
Right. And the number 6 naturally attaches to the students in English. Your brain is applying a linguistic strategy that works flawlessly for everyday reading comprehension.
But it fails catastrophically when applied to algebraic equivalents.
Exactly.
That's a crucial distinction. It's not that these students don't understand algebra. It's that their advanced reading comprehension skills are literally hijacking their math brains.
Precisely. The language center takes over.
So if I'm sitting down for a nursing entrance exam, how do I override my own reading comprehension? I remember in middle school, teachers gave us keyword lists. Like the word total always means add, and of always means multiply. Does that help bypass the linguistic trap?
Actually, math educators strongly advise against the keyword strategy today. Organizations like the National Council of Teachers of Mathematics hate it.
Really? Why?
Because keywords are nothing more than the chip dictionary. For comparative relationships, they actively mislead you. If you just hunt for the word times and slap a multiplication sign next to the nearest variable, which in the Clement study was students, you end up with 6s equals p.
Ah, I see. So the danger isn't missing a keyword.
No, the danger is misapplying it because you refuse to model the relationship first.
Wow. Okay, so if keywords are out, what is the actual mechanism for getting this right? How do we force the brain to stop reading and start modeling?
One of the most successful interventions is the Singapore bar modeling method.
Singapore bar modeling.
Yeah. Before a student is allowed to write down a single mathematical symbol, they have to draw a physical proportional diagram.
Okay, how would that work for the university problem?
You would draw a small rectangular block on your paper and label it professors. Then right below it, you draw a second bar for students. But because the sentence says there are 6 times as many students, you physically have to draw 6 of those professor blocks stacked end to end to equal the length of the student bar.
Oh, I see it. By physically drawing the blocks, you're visually proving to yourself that you need 6 of the professor units to match the size of one student unit.
Yes. You bypass the vocabulary entirely.
You're staring at the truth. S literally equals 6 of the P's.
The visual model forces you to balance the quantities before you ever touch the syntax.
That's brilliant. You know, we keep talking about this massive clash between English grammar and mathematical notation. It makes me wonder if this problem has just always existed.
What do you mean?
Well, spoken languages have been around for millennia, but mathematical equations like the actual x's, y's, and equal signs, they feel much more modern. Did ancient mathematicians struggle with translating words to symbols?
They didn't, actually, because for most of human history, mathematical symbols didn't exist.
Why, really?
Yeah, the X's and Y's we take for granted are a shockingly recent invention. In 1842, a German historian of mathematics named G.H.F. Nesselmann proposed a 3-stage framework for how algebra evolved. And it perfectly explains why our brains struggle with this today.
Okay, walk us through this. How did human beings do algebra before symbols?
The first stage was rhetorical algebra. This means Every single mathematical problem, operation, and solution was written out in full prose paragraphs. There were no symbols whatsoever.
So if you were solving a complex quadratic equation, you were basically just writing an essay.
Precisely. And you can imagine the sheer cognitive load that required. You had to hold all the logic, all the syntax, and all the math in your working memory simultaneously.
It sounds exhausting.
It was, which led to stage 2. Syncopated algebra. Think of this like early text messaging. People started using abbreviations for recurring words.
Like shorthand.
Right. In the 3rd century CE, the Greek mathematician Diophantus of Alexandria used abbreviations for unknowns. In the 9th century, the Persian scholar Al-Khwarizmi, whose book actually gave us the word aljab or algebra, did the same thing.
But they were still fundamentally writing in sentences.
Yes, the math lived entirely within the grammar of spoken language.
Okay, so when did we finally get the technological leap to the math we recognize today?
That is stage 3, symbolic algebra. And it didn't happen until the late 16th and early 17th centuries.
The 1600s.
Yep. In 1591, a French mathematician named François Viet decided to use letters to represent unknowns and constants. Then, in 1637, René Descartes standardized the whole system.
The I think, therefore I am guy.
The very same. He decided we would use letters from the end of the alphabet X, Y, Z for unknowns and letters from the beginning A, B, C for known quantities.
Here's where it gets really interesting. The 1600s. That is yesterday in the grand scheme of human history.
It really is.
This explains everything. Before Viet and Descartes, there was no translation required at all. The math lived entirely in words. We only struggle with translating words to symbols because the symbols were invented centuries later.
Exactly. We essentially invented a highly compressed, almost alien language in the 1600s, specifically to reduce cognitive load.
And our biological brains, which evolved for spoken language, have been struggling to translate our natural grammar into that highly compressed code ever since.
Right. The skill of translating words into equations only became a necessary human burden once there was a symbolic notation to translate into. We are forcing an ancient brain module reading comprehension to interface with a 400-year-old abstract technology.
That is fascinating. Let's bring this historical technology back to the present day, though, and specifically to our listeners who are walking into the TEAS and HESI exams.
Let's do it.
Why do these modern nursing exams care so deeply about a cognitive trap identified in the 1980s or a notation system from the 1600s?
Because for a nursing student, a translation error isn't just a bad grade, it's a patient safety hazard. Algebraic translation sits at the exact intersection of variables, algebraic expressions, ratios, and dimensional analysis.
So in a high school classroom, writing 6s equals p just loses you a few points on a quiz.
But in a clinical setting, reversing a mathematical relationship in a dosage calculation has devastating consequences.
It's literal life or death stakes. If you use the cheap dictionary in a hospital, you could seriously hurt somebody.
That's why nursing entrance exams weight this skill so heavily. Your ability to translate a word problem into an equation predicts your readiness to perform clinical math under severe time pressure when your brain is tired and wants to take shortcuts.
Okay, let's put the listener in that clinical mindset. Give us a classic TEAS or HESI-style dosage problem, and let's work through the mechanics of getting it right.
Here is a standard scenario. You are looking at a chart, and the order reads, a child's medication dose is 3 milligrams for every kilogram of body weight, plus an additional 5 milligrams as a loading dose. We need to translate that sentence into a master equation.
Okay, I am going to avoid Google Translate 1.0 here.
Good call.
Step 1. Identify the unknowns. Let's assign W for the child's weight in kilograms and D for the total final dose in milligrams.
Perfect. Step 2 is identifying the operations and relationships. So what is the semantic meaning of the phrase for every kilogram?
For every signal's a rate, right? It implies a ratio. I need to take the 3 milligrams and multiply it by however many kilograms this child weighs. So that piece of the model is 3W.
Spot on.
Then the phrase plus an additional means I am taking a fixed constant and adding it on top of that rate. So I add 5. My final logical structure is D equals 3W plus 5.
Your model is flawless. Now, consider the clinical stakes of a translation error here. Imagine it's a 10-kilogram child. Using your correct equation, 3 times 10 is 30, plus 5 gives a total dose of 35 milligrams.
Okay, 35 milligrams.
But what if a tired nursing student gets sloppy, relies on word matching, and accidentally translates it as D equals 5W plus 3?
Oh, man. They swap the rate and the constant.
Right. They would multiply 5 by 10 to get 50, plus 3 is 53 milligrams. They just overdosed a 10-kilogram child by more than 50% simply because they mapped it wrong.
It's terrifying. It really illustrates why the semantic meaning has to dictate the equation, not just the presence of the numbers in the sentence.
Exactly.
Let me throw another common exam curveball at you, actually.
Let's hear it.
Let's say a word problem includes the phrase 5 less than a number. My cheap dictionary brain sees the 5 first, sees less than, which means subtract, and sees a number, which is n. So I write 5 minus n.
You have just stumbled into one of the most common reversal traps on these exams. 5 less than a number translates to n minus 5, not 5 minus n.
Wait, what? But the 5 is literally the first word in the sentence. Why am I putting it at the end of the equation?
Because of the semantic meaning. The quantity you are subtracting from, the unknown number, is the foundational base of the sentence's logic, even though it appears second in the physical word order.
Oh, I see. You have to start with the number and then take 5 away from it.
Right. This exact reversal trap is a smaller cousin of the students and professors' error. Test makers know your brain wants to map left to right, so they specifically design phrases like less than or subtracted from to punish the cheap dictionary approach.
It all comes back to overriding the linguistic reflex. What are some other traps test makers use to catch people who aren't modeling the meaning?
A huge one is the word is. Test prep courses often tell students that is means equals. But test makers will use modifiers to change the entire mathematical landscape.
Like what kind of modifiers?
Well, is at least translates to a greater than or equal to sign. Is no more than means less than or equal to. Exceeds means strictly greater than. If you treat every instance of the word is as a bare equals sign, you will mistranslate an inequality problem as a basic equation.
And the numbers might all be correct, but the fundamental reality of the math is wrong. You might be looking for a single answer when the true answer is a whole range of numbers.
Exactly. Another major trap involves multi-step problems, like our dosage calculation earlier. A common misconception is thinking you can translate a problem one independent clause at a time, translate them perfectly, and just shove them together.
You can't do that.
No, you have to pay clinical attention to connector words like plus, in addition to, or after which. Those specific connector words dictate how the independent clauses combine. Getting the pieces right doesn't guarantee the master equation is right if you connect them backward.
Wow. We have covered a massive amount of ground in this deep dive, from the cognitive exhaustion of doing algebra in 3rd century prose to the psychological friction of the students and professors study, all the way to modern clinical dosage calculations.
It's a lot to wrap your head around.
It is. Let's synthesize this for the listener. If someone is sitting down for their TEAS or HESI exam tomorrow, or just facing a dense quantitative report at work, how do we pull all these threads together into an actionable strategy?
It all boils down to actively fighting your brain's desire for the easy way out. You have to build the relationship in your mind before you build the equation on the paper.
Right. Word order is not equation order.
Exactly. You are translating the structural meaning, not the physical sequence of the words. When you see a phrase like a number less than, remind yourself that it reverses the subtraction order. 5 less than x is always x minus 5.
And when we hit those comparative phrases like times as many as, we need to visualize the Singapore bar model.
Exactly that. Identify which quantity is smaller, and realize that you have to multiply that smaller quantity to scale it up and balance the equation. Don't just attach the number to the first noun you read.
Which is so tempting.
It is. Furthermore, stay vigilant with your vocabulary. Watch the modifiers on the word is, so you don't confuse an equation with an inequality. And in multi-step problems, let the connector words be the architect of how your clauses combine.
Building the true mathematical relationship, not just a superficial map. Thank you so much for dissecting the cognitive mechanics of this for us. It entirely reframes how we should look at a word problem.
My pleasure. It's a game changer once you see it.
It really is. And as we finish up this deep dive, I want to leave you, the listener, with a final thought to mull over. We have focused heavily on nursing exams and academic traps today, but think about the everyday quantitative literacy required just to navigate the world and read the morning news.
Oh, absolutely.
The next time you're scrolling and see a headline asserting that, housing prices increased threefold compared to median wages, pay attention to what happens in your head. Ask yourself, did your brain just do a lazy left-to-right syntactic map? Did you just use the cheap dictionary to accept the premise? Or did you stop, visualize the meaning, and build the true mathematical relationship? The stakes for you might not be a clinical dosage today, but your fundamental understanding of the world depends entirely on getting the translation right.